Good morning, welcome, and PowerPoint now. Is it PowerPoint? No. Okay. Very important to, as I said it now, once you identify your thermodynamic system, and we all classified that whether it will be open or a closed, whether it is adiabatic or isolated, everything. Even then, no, you need to know more and more deeper inside every system. In fact, no, uh, every learner, according to a theory of knowledge, every learner is like a blind person. Okay, and a blind person, before entering into the boundaries, no, he has to know in many ways. And generally, people will try to understand one respect. That's how all over the world there is a philosophy of learning represented by this particular picture. The picture says that five blind people were asked to touch an elephant and say the what is the shape. One fellow touches the body of the elephant and says that it is like a wall. One fellow touches the tail, he says it is like a rope. Somebody says it trunk is a snake. And somebody touches the leg, and he says it is like a pillar. Somebody touches the ear and says it is like a fan. So very important. But all are correct. So that's how we need to develop a very thorough understanding into. That's why I'm giving the various levels of understanding what is there inside the system or what is a system in principle. The first level of knowledge, as I explained you in the last class, I'll quickly go through. You need to know how many components, and do the components remain pure throughout the study or are they changing. So whatever I am doing, suppose if I am developing an engine, I am developing a fan, I am developing a windmill or a wind turbine, whatever, I need to say how many components. If all the components remain same purity from inlet to the exit, they are not changing the relative percentages, or new components are not generated, then though there are many components, I can treat them as a pure substance. That's how no, the engineering thermodynamics requires more imagination based on a simple fundamentals. The first one is the components. What is the component? Distinct chemical species like oxygen, nitrogen, H2O, etc. Those chemically different are called the thing. It could be a single component. If it is a single component, there is no doubt it is a pure substance, and the purity will remain same, because only one component throughout means it must be a pure. The second one is a two component. They are called a binary systems. But if the two components by proposition from the beginning to the end are a inlet to the exit, depending on whether it is a closed system or an open system, the beginning to end are a open, then we'll say that binary system. Though it is a binary system, if the purity doesn't change, I can treat them as a pure substance. There is no issue at all. Very important to understand the pure substance definition. As I said it no, a pure substance can become a binary sometimes, then you cannot say that throughout the process it is a pure. I take the H2O, if I go on increasing the temperature beyond a 3000 degrees Celsius or a 4000, somewhere in between, now they'll create the ions. Then you cannot say that it is a pure substance. That's why one need to be careful. To start with, it may be a single component, but if you are ignorant, then there will be something else going to happen. I'll take this example. People not realizing this one and realizing this will have a great difference. Perhaps that example may be too early now. I'll take it a little later. Most interesting. Okay, the next one is a binary system can be treated as a single component. I have given you many examples of dealing with the air. If the purity of the air doesn't change within our system with time or with space, okay, then you don't have to worry. You can create a one gas constant, one molecular weight, one density function of pressure and temperature, the way we do for air. Air, no, it is a pseudo molecular weight. It is a mixture, but still we create a pseudo molecular weight, a pseudo gas constant, etc. This is the example, as I said it, no, we treat many cases of air. That's where we will try to observe. Okay, so suppose if I have a more than 3, then I say a multi-component system. Then defining this system is very difficult. Most of the chemical engineers know study 2 levels of thermodynamics more because their systems are always multi-component, and within their system, no, they are never pure. With time, something may change. From inlet to exit, something may change. So that's how the variations could be spatial. Variation could be time, with time. At time t is equal to 0, entire system has one kind of component. After some time, there is a second component which is coming out because of some reaction. And after some time, there may be third, fourth, or all new components may occur. That is with the time. Okay, sometimes inlet to exit there could be a change. So that's where we need to know some nature of the substance within the system with the time or with the space, how it may change. Okay, so based on that one, a simple working substance is the one, and which will not change because of motion. Acceleration, deceleration should not change the purity of the substance. An increase or a decrease of the viscosity should not change the purity of anything. And the shear, capillarity action should not. In fact, no. Suppose if I want to study the blood flow through the capillaries, etc., one has to be very, very careful of applying the thermodynamics. And strictly speaking, there is nothing happening except that the blood is traveling from a large diameter to small capillary in the brain. Because the blood contains many cells, these cells may get stretched unreasonably and suddenly the properties may change. So those kind of thermodynamic systems are very tough. So that's how in a common engineering thermodynamics, we don't consider them. And those will be considered as a special sciences at a higher level. So idea is these effects will not change the purity of the substance. They are called as simple pure substances. When I heat it, it can change. When I compress it, it can change, but not by these atoms. Perhaps this point is very important to start with. And the next important thing is a pure substance may be homogeneous throughout. Okay, because as I said it, no, I have a two components like air and air, majorly oxygen and nitrogen. If the composition of oxygen and nitrogen is same throughout the system, then I say homogeneous substance. Most of the time, whenever I say it is a pure substance inside a system, most of the time it could be a homogeneous, though there are exceptions. We can take examples as we go ahead. So a substance which is uniform thermodynamic properties. The homogeneity refers to the spatial variation from the inlet to the exit, one corner to the another corner of the system. Those are called the spatial variations. The next is the pure substance. Now you can see this one, the perfectly hardcore definition of pure substance. Again, I am saying again and again, the definitions of thermodynamics always should be used with a wisdom. You cannot blindly by heart a formula because exceptions can happen, and that's how the innovations can come. So you see this one in a hard framework, a pure substance, I'm reading verbatim, a pure substance has a homogeneous and invariable chemical composition. What is the meaning of invariable and homogeneous? Not varying with the space is called a homogeneous. Not varying with the time is called the invariable. Okay, both are talking about the variation. One is with respect to space, one corner to another corner. So whenever I see that in a given system within the boundary, either with the space or with the time, if the composition doesn't change at all, then I can say it's a perfectly pure substance. Again, I take example of wind turbine. You see, the air enters. What is the air? Same composition. And yeah, suddenly I switched on the wind turbine, you say. At t is equal to 0, the quality of the air is same everywhere. After 2 hours of working, air quality is same. And similarly, whatever air enters leaves the wind turbine with the same quality. So in that case, no, I can happily use a pure substance for either wind turbine or a fan which is there in your rooms. The next level of knowledge. Once you are through with the components, then you need to know the phases. Are the phases changing within your system? Or phase is remaining same and nothing is happening too? And it is very important to know the phases more and more with the time. Now, as I said it, no, precisely the phase is a state of aggregation. What aggregation of what? All of every substance is consists of the atoms or molecules at a thermodynamic level. What is inside the atom or what is inside a molecule is perhaps simple engineering thermodynamics will not worry. The moment I have so many atoms or molecules, how they are aggregated together, physically connected together will define a phase which by other means. And this aggregation is homogeneous throughout, then I can say it is a single phase. If the aggregation level changes within the system, then I say that it is a phase-wise inhomogeneous. As a component, it is homogeneous. As a component, it is invariant, but because of the aggregation, there may be a change. As I said it now, you take a cooker. Initially, you pour the water inside the cooker, put the vessel, and you are slowly heating. What is happening? The components are same, single component. It's a H2O remaining H2O throughout. But the slowly what will happen on the top, there is a steam which will build up. Okay, means I am changing the phase. Initially it may be almost homogeneous water, but slowly there are two portions, liquid portion and steam portion. There may be a small portion which will have a liquid and the vapor together in an equilibrium. You need to appreciate. See, whenever you say if the same physical aggregation or a property, then we can say a single phase. Now, how many different phases can we think of? In fact, no, this is the most important. If you can innovate a more and more new phases, and you will get a better products. Something which is not possible yesterday may become possible tomorrow just by innovating a new phase of same substance. I'm not changing the component, but I am finding a new phase of this one. All of vapor, liquid, solid. But within the solid, as I was saying, there are substrates. Depending on the crystal symmetry and the size of the crystal, and strictly speaking, all are sulfur. And chemically they are same. But still, the property of this particular one, okay, and the property of, can I use? The property of this one, physical property of this one may be density or so, and the, how do I, sorry, property of this one and the property of this one. These are different in terms of density. Sometimes, in an Ayurvedic, this particular fellow will work better for a disease, but it is chemically only the sulfur, and this cannot do. Why? By the virtue of crystalline structure, there is extra bond energy which is changing. Strictly speaking, a disease is treated by a bond energy only. That's how the homeopathy doesn't depend upon the chemistry. They depend upon the potential of packing, because that is the one which gives the potential to cure your disease, or sometimes even with the chemistry. Okay, now suppose you see this one, just by changing the phase you can get a greatest benefits. One of the essential equipment nowadays in the house is this one. I need pen now. Okay, now you see, all of you know the refrigerator, and such a powerful refrigerator which changes our lifestyle a lot. So you can cook in the night and eat in the morning or later whenever you want. Not only that, there are freezers. I can eat apples in summer and mangoes in winter. They'll increase the shelf life of any perishable food. Now if you see how this particular appliance is possible fundamentally, and there are many details, but if you see the fundamental concept, if I open up, and there are important parts, like one important part is here. So this is the one, the evaporator or a freezer. Now you see this particular one. Now this is the one, evaporator or a freezer. What actually happens, suppose somewhere if I take this particular point, what I'll do, I'll try to have a low pressure liquid. Any suitable component, I am not discussing about the what kind of component can do. Okay, now this will enter, because this particular liquid is at a very low pressure. All of you know from fundamental physics that lower the pressure, lower will be the boiling point. This fellow can boil even at a minus 5 degrees Celsius or a minus 10 degrees Celsius just by controlling the pressure. Now, this particular one, no, I'm circulating in a big pipeline. So, the number of pipelines, you see, this one. And inside which what I'll put a mix of ice cream, maybe milk, some powder, some flavors, etc. This may be at a temperature of 10 degrees Celsius, maybe 20 degrees Celsius room temperature. Now this is at a 20 and this fellow can evaporate at a minus 5 or a minus 10. Automatically all the heat will be taken from here. Now by the time it comes out somewhere here, this will become low pressure vapor. Pressure will not change much, only all the liquid is becoming a vapor. Because the liquid is changing into vapor, I am getting a benefit. What is the benefit? I could turn ice mix into ice cream. Not only that, I can put a food inside this one, I can eat after 10 days sometimes, 20 days sometime, I can increase the shelf life of this food. You see this one, just by changing the phase of this. But I want this to work again and again. What I'll do afterwards, you have the second one, this particular, sorry, some areas it is not working. So this particular one, you see this one, this is called a condenser. Okay, I am writing here. Actually, I typed it wrongly. It's a condenser. Now, what happens here? Before sending into this condenser, this is a condenser, not evaporator. Sorry. Condenser. What I do? I compress this entire vapor to higher pressure. All of you know, but if I increase the pressure, it will condense at a higher temperature. Now, I select a pressure in such that this temperature will be higher than the atmosphere. The temperature of the fluid here will be greater than the atmosphere. Then what will happen? Because this temperature is higher than the atmosphere, naturally it will lose all the heat and it will become a liquid. So all the heat which I have taken from the freezer, I'll throw it to the atmosphere. Now the fridge will work continuously. To do this one, I need a more parts which I'll discuss later when I am going into the details. What I want to say, many items can be generated just manipulating the phase. The component will not change. It is the same chemistry everywhere. So that's how realizing the phases, using with the phases will change the lifestyle like anything. You assume a steam turbine or some other application just by having a phase change. We see this one. All the living species understood the phase change very cleverly and they live very happily. Let us say we are walking in a hot sun and it is so hot that the atmospheric temperature is higher than our body. And unfortunately, we are doing some metabolism. Our body has to lose heat on an average depending on whether you are working hard or working less. Now the question is, outside temperature is higher than the body, how can I lose? That's how our brain will think and try to pump some of the liquids through our pores of the skin. And these particular water wavelets, they are exposed to the sun and there is a more water will evaporate. Whatever evaporating will try to absorb the heat from the skin, we feel happy. So all the living species manipulate the phases a lot. And more you learn about the phases, more will be the equipment which you can create. As I said, you need a compressor extra. That's how there should be a continuous learning with the phases. So initially we found that liquid, vapor and solid is enough. I don't want to. Because of which we lost something. Okay, let us see developing a display system for a computer. Let us say this is the boundary where I want some display system. When I have some kind of phases, what was the innovation? Something like a cathode ray tube monitor. It was doing the purpose, no doubt about it. But when I depended only these kind of materials and phases, and it was taking lot of electricity consuming, and over and above it is producing a high intensity radiation for the same purpose of reading something. The people were spoiling their eyes. So the people had to innovate that many things can happen. Now what is the next innovation? The people innovated LCD screens. liquid crystal is a new phase. These liquid crystals can serve the purpose of a display, but more economically, more safely. And we did not stop here itself. We try to innovate a new and ideas. The future could be many, something like LEDs. Maybe it is not a new phase. It is a new technology. Very important that one should be thoroughly studying the new phases. More new phases innovation will change the lifestyle, will produce more equipment. So that's where I'll talk about one of the celebrated phase which is changing the electronic lifestyle. Okay, and many electronic devices are becoming very efficient, very compact. All of you know nowadays you can carry the entire computer in your. So no doubt electronics has its influence. You imagine if I cannot find out a liquid crystal, whatever electronics you develop, chips you develop, will it be possible to have your mobile such a small doing everything? It is a LCD screen which solved the problem. 95% of the problem is solved by LCD and remaining 5% is the one electronics, computation, chips. I agree. Those are also material. You imagine that the liquid crystals, within the liquid crystals there are many classifications I am not going into. These have a special kind of crystalline structure. These crystalline structures can change between the solid to liquid. By changing the orientation at a given point pixel, they can change the color. By manipulating the voltage at various points, I can display beautiful pictures or a write-up or anything on a display screen. Then the power consumption is less. You are doing all the computation and the system is very lighter, compact, and you are doing so many wonders. So it is. And the same way, there are many phases which I cannot discuss. The next one is the plasma. In fact, people are working a lot on a plasma based fluid. It is another fifth state of a fluid, more than a gas. If I innovate a lot now, the rockets will be very lighter. You don't have to carry a lot of energy while launching a rocket. There are many purposes. Similarly, there is another phase which is called a superfluid, which will have a zero viscosity. And liquid helium is an example of superfluidity. So the people should understand, and all of you know the glass is another new state, neither a liquid nor a fluid. So that's how, very important to understand finally, a system can have a n number of solid phases and n number of liquid phases. When it comes to the gas phase, they have to mix together, they're together. I cannot separate the gas phase so easily. This is another important thing to realize when we are developing the system. Now coming into, is that sufficient? Just knowing the number of components, whether I can treat this as a pure or impure, or what is the phases, is the phase changing or not, is that sufficient for development, or you need to know more and more to develop it? What more? Next, what else to be known? And in fact, no, this was a turning point in the entire engineering. You believe me or not, till 16th century people thought that just by describing what is inside a boundary, you can achieve your products. You don't have to worry much about the any kind of wonder. You don't have to do much wonders, etc. That's what the people thought. Now let me take to the next level. Your knowledge, your understanding, knowing is much more than the description of a single component, multi-component, is a homogeneous, invariant. That is not enough. You need to grow more. That's where I'll take a famous quote by a great innovator. All of you know, the Kelvin is called a Lord Kelvin. He has innovated one of the fundamental truth of engineering or a science. Zero absolute is the perfect truth. That's why unlike other innovators, he is called a Lord. You see what Lord Kelvin says. When you can measure what you are speaking about and express in terms of numbers, you know something about it. Mean whatever you know, whatever you describe, whatever you understand, if you can give a number to that, it means you know something. Then he adds, but when you cannot measure it in numbers and your knowledge is a meager and no use. And why he said, I'll tell you slowly little later. That's why the next level in the engineering thermodynamics is not just describing what is inside the boundaries enough. Can you give your description in terms of numbers? How do I get a number? How do you give a number to solid phase? Solid phase of 5 units, liquid phase of 10 units. How can you give a number to a phase? Or I can say there is a H2O which is 2 points and there is a H2 5 points. Can I give? Perhaps I need to develop another description which can be given in terms of number. Unless you give any description in numbers, you cannot proceed further. The people worked 100 years to get a small change without knowing a number. The day when we come to know in terms of numbers, the same thing happened in a few months. So the numbers will enhance your knowledge. In fact, no, the people say that engineering is full of numbers. A psychology professor always hates an engineer. Why? This fellow cannot understand anything without a numbers. He needs numbers, numbers, numbers. How can you describe everything in numbers? In fact, you see this one, the purpose of numbers and the influence of numbers. That's where the thermodynamics developed another methodology further. How to quantify a knowledge? Why I want to quantify a knowledge? It answers first. You see this particular one, the quantification. Thermodynamics deals with the changes in the system. I told you the thermodynamics is just by changing a liquid to vapor, vapor to liquid, again and again, a cycle, I am getting a greatest benefit. What is that? I am able to eat mangoes in winter, apples in summer. Something grown in Chennai can be eaten in Delhi. Something grows in Mexico can be taken in Delhi because I am able to pack and transport to anywhere. Increasing the shelf life of food was one of the important development for a civilization. Everybody on the globe very early wanted to develop a technique of increasing the shelf life of every food. So means changing a system is the one my achievement. But to change the system, I need to know what is there in the system. That's why I described. Is it a liquid? If it becomes vapor, I'll get this benefit. And the same vapor should come back to liquid. Why? I have to do again and again same thing going. So changes are essential. Should I only depend upon liquid becoming vapor, vapor becoming a liquid, and single component should stay as a single component? By using that knowledge, can I design a refrigerator perfectly? Can I ensure that when I mass produce 1000 refrigerator, all the 1000 refrigerators will work exactly within the same performance? No. That's where one need to know for the sake of producing a changes. That's how you need to identify a number, a measure for that change. So how do I differentiate the change in a phase by a number? Which number will help me that there is a change in phase? Which number will guide me that how much change in phase is required, how much not to happen? Or I am doing somehow all the fluid is not changing, it's fixed to the vapor. Can I get a number to know whether all happened or if something happened or more happened? That has to be understood through a number. So that's where this will help in estimating the ability. The moment I have a numbers instead of description, then I'll understand this refrigerator is better or this other refrigerator is better. And all the better comparing two different requires a numbers more than a description. That's how slowly we need to move as an engineer a description in terms of numbers. And I need to find out those characteristics which can be given a number. Obviously, without any confusion, can I say this description is better than this, be given a number. So the numerical values of characteristics will completely, and as I said it on, the Lord Kelvin says, if you express in number, then only you can claim that I'm an expert. That particular fashion scientist who is making these perfumes or cosmetics, he wanted to prove that he is the greatest innovator. So that's why what he developed, he along with the Fair and Lovely, he gives a small strip. That strip is divided into 1, 2, 3, 4, 5 colors. He is proving that when you use a Fair and Lovely, your skin color is changing from level 1 to level 5 and you are becoming a fair. Now the people will buy. Before that, people will not get a confidence that actually my fairness increasing or not? You imagine, very interesting that the moment you quantify, your product will be sold because the people think that you know what is. That's where the numerical description of a substance with a known phase. I know it is a solid, I know it is a vapor, but still I want to get a number, or even the numbers can differentiate. What is the obvious thing which can given a number? Whether or not it is immediately useful or not, you imagine. The first thing a human started numbering, I can know this is approximately an inch or so, and I know this is approximately 6 inches, and I used this one, this is approximately, I used this one. So something obviously given a number is the one which doesn't require any theory at all. Okay, the behavior of system may be described in either microscopic or a macroscopic point of view. Something very macro. Okay, so what is this particular microscopic or a macroscopic? Okay, so the microscopic description. Now you see this one. The microscopic description of any system is, after all, what is a substance? The substance contains atoms or molecules. Why this particular system is like a solid or like a liquid, and being a solid also, one case, some of this one, why it has this kind of shape? So all is because of the behavior of the atoms or molecules, how they are arranging themselves. Means strictly speaking, no, a liquid or a solid or a vapor or a single component or a multi-component, a change from one component to another component or one solid phase, one phase to another phase, all can be described only by knowing the behavior of the atoms and molecules. Suppose if somebody express everything in terms of these particular molecular behavior, this is called a microscopic description. But it is a very tough. Using this in a regular life or engineering life is almost impractical. Let me say, but there are some thermodynamics which are called a statistical thermodynamics, and where no, all the description of matter inside a system is done only with respect to what is happening to atoms, what is happening to the molecules. That's all. They'll not care about anything else. That is called a microscopic description. Okay, you see this one, microscopic description starts from the truth. What is the truth? Every system is having a substance. What is after all a substance? Collection of atoms or molecules. That's all. And why system is changing? Because atoms and molecules are behaving. Why a solid is becoming a liquid? Because the bond between the molecules changed. Initially it was so rigid, now it is flexible. And why a liquid becomes vapor? Initially the molecules are moving, but their distance between two cannot change a lot. Now I have taken to another thing, each molecule can freely move around without bothering with the other molecule. And if the intermolecular forces are zero, then I say ideal. Everybody is a free bird. So you see this one, most of the behavior can be explained through. Each atom can be described. The moment I have an atom level, every atom will have its own position and velocity and the mass. Now I can go on describing with respect to why the solid is solid. You see this one within the perspective of this. Okay. Now let us say this is one molecule, this is another molecule, and this is another molecule of the solid. And all these molecules, their center is almost fixed. They can vibrate with respect to this one or in the x direction. So at any given time, I can have what is its xy position, what is the please. Okay. Now you see this one, the most powerful way of describing the state. Okay. So I take a set of atoms arranged inside a solid phase. Okay. Now in between there is some bonds. These bonds like a springs or so, that is what the understanding model. Okay. By doing something, what I am doing, some kind of change of state or anything. Suppose if it is a solid, each atom will have some x and y position, but they are not rigid always. What will happen? This particular atom will vibrate with respect to the center position. Okay, then automatically it will have some velocity xy prime, and this may not vibrate with the uniform velocity because it is almost like a harmonic. In a harmonic, velocity will never be uniform and it is varying with the time. So that's how it can have x prime, y prime. Means each atom having some kind of displacement, some kind of velocity, some kind of acceleration is responsible the behavior called a solid. Okay, suppose if it is a liquid, then I need to take in a vessel, without that I cannot contain. Then there will be a fixed surface. The molecule cannot escape above this fellow. But within this one, no, they can randomly move anyway. But this fellow cannot move randomly in a solid molecule. But it can facilitate, vibrate about a mean position. The moment the same molecules become a liquid phase, number one, they cannot cross a boundary because there are some attractive forces which will keep them together. Nothing can go unless there is an evaporation. Lot of energy is required for that. But this fellow is not as rigid this. This can move at any point. Okay. Now again I have x function of time, y function of time, maybe 3 dimensions z function of time of each molecule. Now this molecule will have a velocity x prime, y prime and z prime. Okay. So now then I can have the acceleration, etc. Means why a solid is becoming liquid, I can say that the displacement, velocity, acceleration levels of a molecule have increased suddenly because of something, maybe heating, maybe something else, whatever may be the action which made, now they have a vigorous displacement, vigorous velocities, vigorous acceleration. Means everything can be described in terms of knowing what is happening to the molecules. Now the question is, if I have a small 1 centimeter by 1 centimeter by 1 centimeter system, how many molecules it will have? And each atom requires 3 equations, one for the displacement, one for the velocity, another for the acceleration. And each displacement has a 3 x, y, z coordinates, and such an atoms will be billions and billions. Means just to know a phase, I need to solve billion equations. I need a supercomputer to know whether a given thing is a solid or a liquid. But this is the truth. Why solid is a solid? This is the truth. This is the fundamental truth. Nobody can challenge that. This is not the truth. But this makes engineering very, very costly, almost impractical. Go back. Okay, so now you can see this particular one. Instead of that one, if I go to, or let me see, the collective description of atom is the description of system. All the atoms inside my boundary, if I describe all of them, then I can just say, I have completely described the system. By knowing all of them together, I can understand it is a single component or a multi-component. Is the phase changing or not, something happening or not, all can be done. And each atom requires 3 equations for description of position, as I said, 3 for the description of velocity, 3 more for the acceleration, 9 equations for each atom, and how many atoms per centimeter cube. Okay, so highly computationally intensive. To know ordinary truth, you are working for 10 days to know whether it is a solid or a liquid, even in a supercomputer. Perhaps that requires there are things. If you see, a molecular dynamics is one subject. Kinetic theory is another subject. All of you might have learned kinetic theory of gases, kinetic theory of substances in a fundamental physics. Even the temperature is defined as kinetic energy, microscopic kinetic energy of atom or a molecule. And similarly, there are statistical dynamics, which will use a probability theory to understand. These are the ones. So strictly speaking, the truth is this: a true description of any system is supposed to be microscopic. but it is impractical. I cannot use this one to design a refrigerator sometime, design a fan sometime, design a wind turbine sometime. You imagine, I am solving a wind turbine and I have taken some diameter of the wind turbine. I need to care how many billions of wind atoms are coming and what is the xy z coordinates of each atom. What is their velocity? Is it a uniform velocity or a changing velocity? Do you think it is possible to design a wind turbine in a finite time? Perhaps impossible. But this is the truth. There are some people who will always know about the truth. That's why the engineering, this is what is called engineering in the thermodynamics. People say sometimes a classical thermodynamics, but we have used. In fact, no, it is because humans studying in this system, the thermodynamics is like this. Suppose if a monkey or a donkey studies thermodynamics, they may use a different totally. Why? You see this particular beauty. What is the macroscopic description? We have some senses. I can touch it, feel it. I can see it and feel it. I can smell it and feel it. Based on that one, I'll take a decision. By touching, whatever I can sense, that is a property. Or that is the one which can be given as a number. Whatever I cannot sense, I will not give a number. Now suppose if the dog is a study, dog has a powerful smelling than vision or a touching. That's how it will say everybody. In fact, no, I'll give you a small incident. I was going for a coffee with my colleague, and whenever we go for a coffee with that colleague, most of the street dogs will come and start smelling him. Then I was wondering, what are you doing? Why dogs are after you? He has a pet dog. That's why all the dogs will come and smell and wish something. I don't know, thanks for helping one of my friend. Or it may be, they may be saying, you are unnecessarily hiding my friend inside your house. I don't know what do they say. So the description depends upon the senses. All the engineering thermodynamics which we are giving a numbers based on our senses. It's a very superficial. In fact, you see this one, the engineering thermodynamics uses macroscopic description. And whenever I say that, I need to have the senses. My senses will say, better to measure, give this characteristic as a number, then develop an instrument to get a number. Okay, and so the gross or average effect of many molecules are described. So indirectly, no, these senses, all of you know why when I touch some body it is hotter, because atoms in that body are vibrating with a higher amplitude than my body. That's why my body thinks that is hot. But I'll not measure what is the amplitude of vibration, how many molecules are vibrating, I'll not do. But I'll take it as that I say it is a cold or a hot, very macroscopic. And I'll try to give a number for that cold or a hot. So that is called a macroscopic description. This description is time averaged influence of many molecules together, giving some impact to your fingers. Based on that one, you say that this is this much hot or this is this much cold. So this is the one. Engineering thermodynamics depends upon a virtual description. There is no truth in a degree of hotness. It is a totally virtual, but still it is highly practical. Why? Because we humans have some senses. We can design, use, enjoy according to our senses. That's how any quantification or any numbering based on what I can sense, what I can feel is the true engineering. Otherwise, I don't care at all. Many times we have hardly any expertise to enjoy the smelling based. Most of the engineering systems, there are very few engineering systems which are based on the smell perhaps. That's how the people started. As I said it, no, it is the macroscopic sense made us to define the property. That's what I said it, no. I used the this way, this has some specific length. I started using this one, this has specific, and this. That's how, strictly speaking, when I say here to here, do you know how many number of molecules are here? And what is the space between these two molecules? If I say my hand is of this length, that entire length of this hand is not having the matter. Sometimes there is a gap between these two molecules. Even then, I'll say my object is of this length. And based on that, I buy, sell, I take a decisions. You see first one. So a macroscopic field is length. Length is the one which is very easy to feel. That's how very early the human started taking a decisions based on the length. Okay. Now you see the moment I know the length, I can create the secondary thing area. Is a length which gives me some kind of estimation for the area and also volume. So this became the first property, or anything which we want to give a number. First we give a number in terms of either length or area or a volume. Based on that, we try to judge whether it is this kind of substance, that kind of substance, and this is the first. And this doesn't require any law at all. In fact, we forced this one inside our engineering life so much that Einstein started to question, this length is stupid. As long as you move with a velocity less than the speed of the light, the length 1 centimeter has a meaning. If you move faster than the light, automatically the length changes. This same 1 centimeter may look 3 centimeter, 5 centimeter. It's ridiculous. Why it is ridiculous? Because you are taking an engineering decision or a numerical number based on your senses. The day your sense gets cheated, all your engineering will fail. But still, this is the convenience. The next important thing. So based on this length, we have used the solar clocks, time clocks, everything created a time. Strictly speaking, you see very perfectly how are you measuring a time. Just by knowing the change in length or so, you know very well how the initial clocks are generated. Some displacement, some length changes. Okay, the moment I have a time and length, then I'll get the second one, velocity. So the velocity of there is a let us say truck which is carrying the gasoline, and the truck is moving with a velocity, and I say that entire gasoline will reach Bombay to Delhi in 2 days. Is that true? Each molecule will move in its own velocity, its own acceleration, but we don't care. Because this entire system, I could describe some one length changes, one position change, I am giving a one macroscopic quantity. I can get an acceleration. Then I can automatically get the required. So all of you know how funny, how do I define a mass? You take a body A, body B, balance their displacement using a simple balance. This is equal. And now I'll give a one number to known mass. Another mass is, if it is equal, then I say this is also 1 kg. This is also 1 gram. Strictly speaking, the mass is innovated. Mass is numbered only by displacement. You are taking a relative displacement of one known and unknown. When they match together, this equal to this mass. You see this one, most of the macroscopic. Strictly speaking, do you actually add how many atoms? What is the mass of each atom? Together will be total mass, but we don't care. How many atoms can make 1 kg? Many of people will not know, but still will make. The moment I know this one, because I know from the senses length, the length gave me area and velocity. The same length helped me to get a time scale. The moment I know the time and length in a macroscopic sense, I created a velocity and acceleration. The day I could get the mass, I created the force. And the great Newton helped us how to develop a devices based on these senses. And the force per unit area, again pressure. So to develop this one, I needed no theory at all, no law at all, because this is the sense which is the most powerful with me, powerful with the humans. The macroscopic behavior is inherently a psychology of a human. The entire engineering thermodynamics got a shape of this kind because the humans are studying. If any other species science, perhaps the thermodynamics will be different. Okay. Any questions? No, no. Okay. I'll just, now you see this one. No? Yeah, yeah. Hello. Yeah, please. Audible but not clear voice. Can you try again? Hello. 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 voice is not clear. Can you type? Uh-huh. Any other? Hmm. Yeah. So the grass behavior, let us say I'll give you an example. We say the pressure is 1 Pascal or a 1 kilopascal. What is actually the molecules of a gas are continuously hitting the wall of a container, and 1 kilopascal is due to so many molecules colliding with the wall per unit time. This grass effect is 1 kilopascal. But do you know exactly how many molecules should hit in 1 second at what force to get a kilopascal? You don't know. But we have developed a quantity. The grass behavior of all the molecules bombarding on a wall is taken as a pressure. It's a grass behavior. Because I can feel with my senses, sometimes if the gases are bombarding more, I see that I'm getting a pinch. So it is more. When they are sucking, then I say that it is a lower than the what it is, negative way I created. This is a grass behavior of all the molecules and translated into number. But even now we don't know perfectly, in order to get a 1 kilopascals, how many molecules should hit per unit area per second. What acceleration? We don't have. That is what the statistical thermodynamics try to understand. Can I have a one-to-one correspondence? But there is no doubt, higher the number of collisions in a second per unit area, more will be the pressure. Lesser this one, less will be the pressure. But it works. It's a macroscopic and a grass behavior. Okay, in fact, no, the next class we'll see this one, a temperature. One of the beautiful, the powerful macroscopic temperature, but totally pseudo. Only because of our sense, but it does wonders. But the temperature is such a concept which is totally based on the human senses. Highly grass behavior of so many atoms, but a very powerful way. Our entire day-to-day life will work only because of the temperature. I'll continue next class. A beautiful story of a temperature, the best way to quantify the behavior of system. Okay, thank you. One more question? Yeah. Yeah, as I was telling, if you recall last class, I said it. See, I have some purpose to solve. As I was giving you an example now, I have a computer. Whatever is happening in the computer, I want to see what input I am giving, what output I am getting, or in between what is the calculations coming, or any kind of music, or any kind of picture I want to see. So now the question is, in this particular area, I want to have a display system. So I need to say that I need a screen of so many inches. You take a decision. So in order to display something inside this boundary, now I need to know what kind of material will help me in displaying. And to get the display, what should be given inside the boundary? What comes outside the boundary? You see that any display system which we have, the electricity is input and output is the radiation distribution with the different frequencies, different intensities. Sometimes same color with low intensity I don't like. The same color with a high intensity I'll like it. And the same intensity, this color I say yellow, are not at all visible. Give me in some other color, means frequency. Now you are enjoying all this, but within that particular boundary, you are trying to enjoy what colors and what intensities. Then initially people thought that only way of solving this one is a cathode ray tube. For creating a cathode ray tube, you need to have a high voltage. You take a gas which gets ionized. When it ionizes, no, it will get the colors and display. That was the cathode ray tube. It dissipates a lot of heat. You need a big air conditioner even for a PC. And then it consumes a lot of electricity. Not only that, it produces an intensity much more than reading. Unknowingly, you are burning your cells in the eyes because you are subjected to more intensity. That much intensity is not required. Your eye to get a signal, it's red. Or he is writing my name Subbarao, that's all. To know that each display is just a Subbarao, if it is a more intensity, I am burning my eyes. That's why within the same boundary called a display system, I try to innovate a new material. New. So that's how, what is your target? Are you developing a display system? Are you developing a computer chip? That is the one. Whatever is your object, target, that is your system. How do you isolate? You need to know exactly up to what extent you want to display. This is what exactly happened. When the CRT monitors were there, then you get a high intensity in the entire room. Whether or not somebody is studying in that corner, there will be an intensity. The moment you go to a liquid crystals, there is an angle of co-vision. Within that, the intensity is good. All of you know, you go to your own LCD screen, you look at a 180 degrees, you see nothing. Even in a mobile, why the mobile, no, I am reading, I should know. Whatever I am doing is my personal matter. Why should he see? When I am working with the mobile, a person sitting aside, because he gets a very long angle vision, he can't see what is there in the screen. All these things are purpose. What is the boundary? What is the boundary in which you want to radiate to read is also, and who will, the expertise has to come up with what you are aiming to. And in fact, no, this is the one, looks a simple definition, lifetime you are doing. Sometimes you will draw a more boundary, waste money. Sometimes you make a boundary too small and suddenly you think that you have done a wrong thing. I gave the example of drawing a boundary with the chlorofluorocarbons in the first class. This is the same thing. The second question. Why is considered to be isolated system? Yeah, I answered this one last time also. When you have no surrounding, then it is an isolated system. We think that the entire university is unique. There is nothing interacting with the universe, this universe. All of you know that this is within the scientific perspective. If you take any religion, which is not true, the people say that there are two universes which are interacting together. But within the scientific sense, I have considered everything which I know of, and I have considered so much that there is nothing surrounding. That's how the universe is an isolated system, because I have taken everything inside. So a system becoming an isolated naturally because there is nothing to interact. What is an isolated system? An isolated system is the system which will not interact in any way with the surrounding. When there are no surroundings, no interaction, naturally isolated. It's a sake of understanding or defining something. Okay. Thank you. We'll